Hello everyone, in this video I'm going to talk about this question. Why do physicists call the negative of a potential function as the potential energy? So let's break it down together. So suppose that we have a curve C with initial point A and the terminal point C, and suppose that this curve has a parametric form, let's call it R of t and t between A and B. Therefore here we have R of B and A is equal to R of A. And also suppose that F is a force field that moves an object along C, right? Now, according to Newton's second law, we have F is equal to the mass of the object times acceleration, right? And in our case, acceleration is going to be R double prime of t. Now, let's compute the work done by F. So we denote it by W. W is equal to F dot dr. So, and this is going to be, by definition, this is going to be F of R of t dot product R prime of t dt, t from A to B, right? So what is F of R of t? This is going to be M R double prime of t, right? M is constant, therefore we can put M here, and then from A to B, R double prime of t dot product R prime of t dt. And now, instead of R double prime of t dot product R prime of t, we can put 1/2 R prime of t dot product R prime of t. You can easily check that prime. So you can easily check that out, that if you consider the derivative of this is going to be 1/2 R double prime of t dot product R prime of t plus R prime of t dot product R double prime of t. And you know that in the dot product, the order of vectors doesn't matter. So therefore here you can consider this one as R double prime of t dot product R prime of t. Therefore here and here you have 1/2 R double prime of t dot product R prime of t, right? I hope that you are now convinced that so R double prime of t dot product R prime of t is equal to 1/2 R prime of t dot product R prime of t prime. So now therefore, so I put 1/2 here M, and now I have integral from A to B, R prime of t dot product R prime of t dt, and here prime. Now by fundamental theorem of calculus, what you have is 1/2 M R prime of t dot product R prime of t from t is equal to A to t is equal to B. So, and therefore you know that R prime of t is speed of is a velocity at the point t. So therefore here what you have is 1/2 M, so the length of v of t, right, squared t from A to B, right? And here, therefore, what you have is going to be 1/2 m the length of b squared minus 1/2 m length of speed of the speed of the object at the point t is equal to a squared. Now this somehow rings a bell to us, namely this is gonna be kinetic energy at the point t is equal to a. Therefore here we have kinetic energy at the point b negative the kinetic energy of the object at the point a. Okay, now on the other hand, suppose that f is suppose that f is conservative. Okay, if f is conservative, so therefore this integral now is gonna be integral of the gradient of f dot dr, right, over c. And now this is gonna be f of r of b based on the fundamental theorem of calculus for line integrals. This is gonna be f of r of b minus f of r of a, right? Okay, what do we get? So we get that this is equal to this, right? Instead of r of b, I can also write down r of f of b minus f of a. So, okay, what do we get so far? We get f of b minus f of a is equal to the kinetic energy at b minus kinetic energy of the object at a. So now now this implies that, okay, kinetic energy at the point b. Now I'm going to shuffle in things around. So negative, so f of b, so I put f of b here is equal to, and I move kinetic energy in this part of this equation. So therefore what I have is the kinetic energy at a negative f of a. Now if I set the potential energy is equal to negative f, right? What we have is this. What we have is this. The kinetic energy at the point B plus the potential energy at the point B is equal to the kinetic energy at the point A plus the potential energy at the point A, right? So therefore F is conservative, so the energy is conserved, right? Why? Because the kinetic energy at the final point, at the point B, plus the potential energy at the point B is equal to the sum of kinetic energy and potential energy at B. And that's why we call this vector field is conservative. It means that this is conserved the energy. So I hope that you like this video, and thank you so much.